There's this well-known truism that I've even heard on stage at QCon before this year, that software's eating the world. And if that's true, it puts us in a position of unique responsibility. What we're telling everyone, we're telling our family, we're telling the government, we're telling people we've never met, that it is safe and advisable for them to let us encode their economy, their culture, their healthcare system into programming languages. Right? We're saying that this is a good thing, and we're saying it'll be good because it'll make it web scale, and they'll say, what is web scale? And we'll say, well, don't worry about it, it's very good. It's good that we're doing that. But I think, at least at our stage in the software industry, we're not really mature enough to fully bear that responsibility. So if you say that software is eating the world, you might say that it's not really paying attention to the taste. Right? It's not really doing justice to the things that it's consuming. And by that I mean that almost all our efforts as an industry are around coping with problems that we have created rather than solving the problems of the world themselves. So you can tell by the names of things, right? Because they're almost always negatively named in contrast to the previous thing we told people was good. Right? So immutability, oh, that's good because we used to do this thing with memory where we changed and it wasn't so good. Serverless, why is that good? Well, we used to have these things called servers and now we have all these problems with them, so we're trying to fix it. IoT security, well, we've connected your fridge to the internet and now it's mining Bitcoin. Right? And you're like, Bitcoin? Are you trying to put money into digital? I'm like, yes, it will be awesome. Right? But I don't think we really necessarily pay proper respect or attention to domains other than ourselves. So I think it's very solipsistic. So one of my hopes is that by the time I retire in a few decades hence, that software will be about what it's about, not about other software. And don't get me wrong, I really like talks about software. Like, I like being a programmer. I think most people who are programmers do. But if you went to I guess I think of these kind of things as not so much conferences as festivals, right? If you went to a literary festival, you wouldn't find an author who was on stage talking just about typesetting or their routine for how they get up and make themselves write every morning. You might find some of those things, but you'd also find them talking about the actual subject matter. If you went to a music festival, right, you wouldn't find every song to be about writing songs. Maybe you'd find some clever ones that were, and maybe they'd be interesting. But a lot of them about other important things, like politics, love, things like that. So what I'm going to try to do today is not to give you a talk about software. So in order to make Sid let me give it to you, it needs to be through the medium of software. But in this talk, software is not so much the kind of the subject, but the medium of expression, the paintbrush, the instrument. So I said that we'd be talking about music, so let me show you some music. So this isn't really music, I guess. This is notation. Right? This is a way of encoding music so that it can be understood. And it comes from a very specific cultural context. If you're part of the European musical tradition and you want to be part of an orchestra, you want to play with a lot of other people, everyone needs to understand exactly what's going on, and so you need to know what note to play at what time. So probably a lot of people in this room will already be familiar with, roughly speaking, what this means, but just to be a bit more specific, every dot represents a sound, and the height of the dot on the stave represents the pitch. So higher dot means high pitch, and the horizontal position tells you when it happens. So you can kind of see, if you trace that melody, da 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 da, right? And so it's really quite close to a graph with just two axes. So this is really well suited to its purpose. So I'm going to claim that it's a regular language in the sense of regular expression. So it's one that could be evaluated in theory on a finite state machine. And that's because musical notation is designed to be executed on a peculiar kind of finite state machine called a musician. So if you're there on stage, right, you do not have time to unbundle nested layers of abstraction and recursion, right? The kind of, however many layers it takes to play a video on YouTube, right? There's all these different layers of abstraction that are unwinding back down to the CPU. If you're a human reading this notation, you don't have time for that stuff. You just need a literal notation that maps one dot onto one note, roughly speaking. And the problem with that is that it can't express abstractions that aren't common to the whole genre of music. If you want to add a new symbol to this language, you can't do it in the language itself. If you want a new kind of mark that means that you want all the people to kind of hit their violins with the back of the the bow to make a percussive sound. You can't do that in the language itself. You can't extend the language. But if we use other kinds of notation, for example, programming languages, we can do that. And so that's the concept of the talk. So I'm going to do these examples in Clojure, but that shouldn't really concern you. I'm just going to be evaluating code from my editor and just showing you the results. So hopefully the actual nature of the programming language is not really material to the understanding. So I had a good friend who I was talking about an upcoming talk, and her advice was never ever do live coding. And then her second bit of advice was, well, and if you are going to do live coding, make sure it's just kind of a small bit. And then her third bit of advice was, and if you are still going to do that, make sure it's not in an unfamiliar language to people. So I'm going to break all three of those pieces of advice, and I hope you understand, because the point of this is not to be about the programming, but about the music. So if you see this little routine thing here, this paragraph of code, this defines an instrument using the overtone synthesis library, and it takes one argument, which is a frequency, and just plays a sine wave at that frequency. So hopefully it won't be too loud, but I'll play this. A little bit too loud. Sorry. Could you turn the sound down a little bit? Thank you. And so what that means is that the sine wave is oscillating at 300 times a second. So if I do it 400 times, whoops, sorry. It's higher. If I do 100 times a second, it's lower. Right? And to prove to you that it is in fact a sine wave, well, what would happen if we had two sine waves that are very close together in frequency, right? You'd expect alternating patterns of reinforcement and interference. So one and another. You can hear that throbbing, right? So that's the sound alternately reinforcing and getting out of its way. But sine waves alone aren't really good enough to model the music I showed you earlier, because notes happen at a particular point in time. Like a sine wave is forever. So this second thing that I'll write here is called beep, which takes two arguments, both the frequency and the duration. So we play that, the note will last for a certain length of time, and then we'll use what's called an envelope, which controls the amplitude of the sine wave, and as it shuts, that means the note's fading away. So let's play beep. Cool. Cool. Right, so my aim is to continually accrete these different levels of abstraction so we can get back towards that piece of music that we originally saw. So the reason why the sounds that we've heard so far don't really sound so realistic, they kind of sound like they might come from a video game or a cheap piece of electronics, is that a real piece of sound does not consist of a single sine wave. So if you have something that resonates 100 times a second, in the physical world, it's also going to a lesser extent, resonate at 200 times a second with a kind of a second wave that's half the size. And it's also going to resonate at 300 times a second. So you're literally going to have a harmonic series of different frequencies that are superimposed on each other to make the sound. So again, I don't want you to trust me on that. So this is a slightly more, well, a very more complicated instrument called a bell. And so what this does is this not only has the frequency and duration, but has the proportions of the different members of that harmonic series. So the H0 is the bass frequency, and then H1, H2, etc. So you can kind of see, if you look at the numbers on this line, that they're slowly fading away. So the higher harmonics are not as present. So when we mix all those together, we get something a bit more realistic. All right, so this is the beep. This is the bell. And in fact, we can do slightly better, because what I've done so far, you can even see with a commented out bit of code, is give you pure harmonics that are exact multiples of the bass frequency. But it turns out that bells, because of the way they're built, the higher frequencies are actually not following the harmonic series exactly. So we go up to the one that's 4 times the bass one, and it actually resonates at 4.2 times the bass. And the one that's 5 times, is actually 5.4. So if we model this in our synthesis code, we'll get an even better bell. right? It's much more realistic, and your memory of hearing bells is being activated by that pattern of harmonics. So speaking of things being activated by harmonics, I'm not going to go into this topic too deeply, but I've spoken so far as though music were physics, right? An abstract Platonic realm, but really it's a signal, and so the interpreter of the signal is very important to the end result. So I've just got a quick little demo to prove that. So I've got 3 little function invocations of the bell. So 600, 500, and 400 hertz. So high, medium, low. High, medium, and low. Right? Now, the trick with this is that I'm actually passing additional arguments to 2 of the 3 calls. And what they're doing is setting the harmonic of the bass frequency, in this case, to 0. In other words, of the harmonic progression, the first one, the theoretically most important one, is being completely dampened by this invocation. And in this invocation here, the second one, both the bass one and the one that's double the bass frequency are being set to 0. So where it sounds high, medium, low, you actually got the bass frequency of this call is 600. The lowest frequency of this call is 1,000 because we've wiped out the 500 one. And the lowest frequency in this call is actually 1,200 because we've wiped out both the 400 and the 800. But it still sounds, assuming I've primed you well enough, high, medium, low. Right, and the reason that should at least work is that that phenomenon of physical sources of sound having a harmonic series in the sound they produce is something that your hardware is aware of, right? You, as a human, encounter many situations where that's the case. So it turns out you can error correct. So your mind can actually replace or infer what the bass frequency should have been. If you can see a sound that looks like it goes 200, 300, 400, 500 hertz, that implies there should have been a 100 hertz sound underneath it. It's quite important because, for example, if you're listening on really small speakers or to an old mobile phone, that might not be able to reproduce the bass frequency of the voice of the person you're talking to. But you can still reconstruct it because you as a receiver know enough about what sound should be. So the puzzle, I guess, I'm left with so far is we know that we have frequency, which is what controls the pitch. We know we can block it out for particular periods of time. But if you take any real instrument, or at least most real instruments, you don't see a slider, right? This is, in some literal sense, a digital instrument in the sense of discrete. So instead of being able to slide the frequency and play anything on the frequency spectrum, I have to push specific buttons. So what guided the choice of the instrument maker to provide these buttons and not other ones? Well, to understand that, you need to know something about what an octave is. And I won't get too deeply into it, but basically an octave is when you double the frequency of a note. So when you go to, kind of sounds like the start of Somewhere Over the Rainbow, right? So whenever you double the frequency of a sound, you move up the next octave, so a C in one octave becomes a C in the next. So in some sense, when you're listening to that melody, you treat it as equivalent. This is close to being a universal in musical cultures, but it's an aspect of how we interpret sound, not the sound itself. So if you play a little kind of melody, and then you shift it, doubling the frequency of each note, you can detect that it's a different melody, but it is in some sense equivalent. So if you accept that every time we double the frequency, we have an equivalent note, what Western music does is divide that doubling into 12. So some Arabic scales do 24, so it's not, again, it's a cultural choice. But if you divide the distance between one note and the next one up by 12, that means each jump is the 12th root of 2, each time you go up one. So we can express that in code quite easily, right? While being faithful to the domain. So if we look at this little bit of code here, this converts from MIDI, which is a numbering system that gives an integer to every key, through to frequency, just by multiplying by 12th root of 2. And so if you convert 69, which is concert A, it comes up as roughly floating point arithmetic aside, 440 hertz, which is what it's defined to be. And if I increase the number, so I go up to the next one, that's 466.2 hertz, which is the 12th root of 2 by 440. So by the way, 440 is just an arbitrary standard. It's relatively recent, like when you standardize on voltage in a particular country. There was a certain period of time when a C in one orchestra wasn't necessarily the same as a C if you go to another country. Cool, so we can automate that. And so now we can actually do a better version of Bell that doesn't take a raw frequency, but you just give it which button you want, and it plays that note. So we have this new function ding, and if I play ding, oops, we get the same effect as when I was playing the adjacent notes on the melodica. So we're getting closer and closer to the domain in theory. So there's probably a little bit too much code on this slide, so I'll walk you through just a little bit of it. But again, we'll be using this in action soon, so feel free to let it wash over you, and we'll get to the actual music again shortly enough. But this is kind of just a mini framework that I'll need to do the rest of the music and the talk. So a note is by definition just a structure that has a time and a pitch in this little system I have. So it's just, this is Clojure, so this is the way you define a map. The keys are the yellow ones, and this is the value. We need a function called where, which applies a function to one of the elements of a note. So you could say where time is doubled or where pitch is doubled. And we need this function from, which seems almost so trivial that you might not really think it's useful, which just creates an offset function. So if I go from 4, that returns a function. If I go from 4 of, whoops, that wasn't what I meant to do. If I do from 4 of 80, I get 84. So it's just kind of building a translation if you think of the graph. So now I can start doing more interesting things and creating more and more abstractions. So I can create a play function that just takes a whole bunch of these notes that have time and pitch and plays them. And I can even do other things, like for my own purposes, I can create an even melody function that doesn't really have a distinction between time. It just plays a set of notes with exactly the same space between them. So even melody of the notes from 70 to 81 sounds like. Cool. And you notice, by the way, that we are, if you're a Clojure programmer, just using a lot of standard library functions here, right? So range is just a way of creating adjacent integers from one to another. So I'm going to play this again, and this is going to lead us into the next thing that's wrong with our music. So it kind of sounds logical as a sound. You kind of know what to expect as the next note, but it doesn't sound like something that is in an actual song. And that's because there's still a layer of abstraction that we haven't gotten into. So scale, you might have heard, even if you're not a musician. So what scale defines is which notes of the 12 that you could theoretically play in a given piece, which subset you are going to focus on. So in the case of a major key, and I'm starting from this C note, the C major scale is all the black notes and ignoring all of the red notes. So it's a little bit more musical. And the way that you move to different keys is that you substitute in red notes and 4 black notes. So I think we can actually represent that a little bit better in code than in the melodica. So a major scale is defined by the jumps between the notes we include. So there's a double jump between the first and the second note. There's a double jump between the second and the third. Then a single jump. Then 3 double jumps. And a single note to go back. So a scale is defined by a pattern of inclusion and exclusion. So we can just represent that as a function. There are other alternatives, so we can have all sorts of different scales that have different patterns of inclusion and exclusion. So let me play a couple of ones. By the way, when we say that we want C-sharp major rather than D, the difference is our friend from, just an offset at the start. So we're still having the same pattern of notes, but just where the first note is can be shifted. So if we play C-sharp major, then the first note is C, and then we keep going up with that pattern of double jump, single, double, 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 single. If we go D sharp major, we've just got the same pattern of notes, but we've translated it up in the pitch space. We can do a minor key. And that feels quite different, right? It feels sadder, at least I think to people with my cultural context, it probably does. And the only difference is that in minor, we're rearranging the order of our inclusions and exclusions.
Shouldn't it be a 3 at the end?
A 3? I guess a melodic minor rather than harmonic minor. Good to see that there's people who understand the detail, but yes. Let's try like blues, which does have natively have the triple jumps in, right? So the blues scale has a triple jump between the first note and the second, and then a double, a couple of singles, triple, double. So the blues scale sounds like this. Right? What I think is really cool is the pentatonic scale. It comes from a world away from the blues scale culturally, but it's quite similar. So you can see these two lining up. The only difference is the blues scale splits one of the double jumps in the pentatonic scale into 2 single jumps. So I'm going to play them side by side, and I think even though they're very similar, you'll get a very different feel. So this is D sharp blues. D sharp pentatonic. The second one probably sounds like East Asian music, right? Because that's a context in which that scale is used. The chromatic scale, in which every jump is a single jump, is kind of the degenerate case where we just get back to our original pattern of playing every note. Right, so we're now ready to start building some, what you might call real melodies. So this code on the screen is row, row, row your boat. Right? And the way that I've built it in this example case is that we let pitches be a list of the pitches, so row, row, row your boat, and then the durations are the duration of each note. So when we kind of slam it all together, oops. Well, we get data, right? Because we're representing this as data before we play it. So this is just a sequence of the notes, similar to if you'd written it out on a page, but rather than being a visual representation, it's a quasi-JSON representation. So there's one last thing I need to do before I can play Row, Row, Row Your Boat is I need to define a beats per minute function that tells me how long one note is. Because in the same way as we needed a translation function to tell us if we're playing in C major, C is our 0, well, we need a similar thing to multiply the time. I won't go too much into beats per minute, but basically it just multiplies the size. So if one beat takes 100 milliseconds, well, you can just multiply the time by 1,000 to get where you need to be. So this is Row, Row, Row Your Boat. And the nice thing about doing it this way is I now have single point of control over some interesting things in the music. So I can, for example, by taking the bit where I translated or actually stretched the notes over time, I can make that faster if I want. And I could also, for example, play it in E major instead. And so not only can I change things, but I'm making important things about this piece of music directly visible to you. But I promised when I was showing you the piece of Bach that it's possible to create custom abstractions, so for a particular piece or genre. So as an example of that, there's many parts of Bach where you end up with all these adjacent notes, right? So if you see that top line, there's a whole bunch of notes. They sometimes go up, they sometimes go down. They're like a mountain range, but they're all adjacent. So you should be able to take advantage of that to come up with a more concise way of specifying that series of numbers. And so this run function, which is a little bit ugly, does that. But the nice thing about it is that when I've written it, if you see that 0, 4, -1, that means I can just define the peaks and the valleys of the mountain range, and the function will just fill in all the numbers in the middle. So I can play something like, and this. And it should sound a bit Bach-like maybe, or Baroque. And I think this is important because if you were having a conversation with a musician and they had a bit of the music where there was a run of notes from C all the way up to another C, that's how they would express it, right? They'd say there's a run of notes from C up to C. They wouldn't say, oh yeah, there's a C, and then a D, and then an E, then an F, and then a G, and then an A, and then a B, and then a C, right? So in order to get close to how the domain expert thinks about the domain, you have to come up with these layered abstractions. And the music notation wouldn't do it. So this bit here, this melody, is actually a different rendering of the Bach piece I keep flashing up on the screen. It's actually a little bit more than that. So it's not as easily directly apprehendable, although maybe with further research and tinkering around with it, you could come up with a really nice way of specifying it. But the nice thing is I can start to express structures in the music that I observe. So this is all composed using like the concept of runs. So places where there is that mountain range of notes. And the bass part is written using the concept of triples. So if we see this bass part, you end up with these 3 repeated notes a lot. So it'd be really nice if getting close to the domain, we're able to do that. So before I actually start playing that piece, there's another part of that abstraction that I need to explain. And that's the concept of a canon. So a canon is a musical genre from Bach's time, and it can be really neatly expressed as a higher order function. So a canon is when you have some notes and you accompany them with themselves, but you do some kind of functional transformation on one of the pairs. So you have a melody, you transform it, and you superimpose it. So that means that you can have a lot of different varieties of canon depending on which transformation you select. So a simple canon is represented by this transformation. It's just delaying the second melody. So you have one melody, and then you make a copy of it and delay it a bit so they overlap. So we can express that in our little framework language by just saying it's where time is from some kind of weight value. That's how we transform. An interval canon is the direct analog of a simple canon, but the translation is vertical. It's in pitch. So you play the melody twice, one higher than the other. And it's quite nice. You can see the symmetry between this function and this function. They're almost the same, except that one applies an offset to the pitch and one applies an offset to the duration. So the Baroque people got really clever with some of these things. They also did other transformations. So like a mirror canon is when you negate the pitch. In other words, when you put it upside down. So you have one melody the right way up and another melody upside down. And our little framework lets us express that really, I think, concisely and faithfully. It just says where you take the pitch and negate it. A crab canon, so called because in Bach's day, they for some reason thought crabs walked backwards rather than sideways, is the time analog of a mirror canon. So you just negate the time. So you rotate the dots that way. I think my favorite, which is kind of tricky, is a table canon, which is a functional composition of those two transformations, right? So the reason it's called a table canon is the idea is that you would be on the other side of a table from your friend. You would write these dots on a page, and you would both play what you saw. So one of you is seeing it from the other direction, which in other words is 2, flips, one around the x-axis and one around the y-axis. And again, because computation actually can throw light on domains as well as kind of obscuring them, we can represent that really directly by this line of code that just says the table function is a functional composition of two other simpler functions. The reason I need to do that is that the Bach piece of music is a canon, so we're going to need to exploit that structure to play it. But I'm going to start with a simpler canon, which is Row, Row, Row Your Boat. So it's designed that if you play Row, Row, Row Your Boat once, and then play it again with a certain offset, you'll end up with something that hopefully sounds a bit nice. So this is when we have a simple canon with 4 beats offset. Right, so we're able to represent that structure directly in code. I'm going to do something a little bit later that's tricksy, so I'm just showing, I'm not going to hide it from you, I'm just redefining canon so that as well as applying the functional transformation, it also just puts a bit of data in the second part so we can distinguish it. Right, so now we're finally ready to do what I promised from the start, which was to render that piece of Bach in programming notation. So Bach was pretty good at this music business and very good at this canon business. So the functional transformation in this piece of music is the functional composition of an interval canon, so it drops by 3 notes, a mirror canon, so it flips, and a simple canon, so it delays. So when Bach was composing this piece, he had to imagine what not only the original melody would sound like, but when you apply those 3 transformations to it, what that would sound like as well, and the superimposition of both of them. So let's do it without the canon to start with, just so you can hear how kind of nice the melody is on its own. You hear that bass and triples. With the functional transformation, so we're hearing 2 copies with a delay and a translation in 2 dimensions, it sounds like this. Whoops, no it doesn't, so I need to reevaluate. Now it will sound like this. Rendering in code. So we're not finished yet, we can keep messing around with this for a while. So it's a rendering in code of these dots. But because it's data, we can also do other things like actually graph it. So let's see if I can get this to work. So you should be able to see visually the reflection, right? So you can see that it's been translated and shifted down. Because once we're in kind of programmatic territory, we don't have to settle for just one representation. We can pick one that suits us. But we also don't need to settle for one particular key or one particular way of presenting this music. We can quite instantly experiment with what would happen if we made changes to the structure of this song. So if, for example, we wanted to play it faster, we could. If we wanted to play it in A instead, I'll play it in a minor key. There's a reason why I'll not play it in blues, but we can chat about that later. So this is what it sounds like in minor. Probably a bit too fast. Right, so you've got this control. You've got this ability to, I guess, just like if you're using a REPL or some kind of instant feedback system, like a hot reloader or your unit tests, you've got this ability to experiment and understand what comes back. You've also got this ability to start leveraging other tools that we have, like version control, right? So you can start to I've done so many iterations of messing about with this, and I've always been able to, no matter how badly I've messed it up, easily just do a git revert back to the earlier version. And if you want to check out the code from this, it's all on GitHub. So I still have one more thing, because it's quite easy to cherry pick a particular moment in history where composition was very functional, right? And there are some periods in history where it's easier to do it and others that would be hard. But this is not really performance as such. I just played it for you and it happened in front of you, and that was cool, and you believed it because it was happening right there. But it's not really a performance as such. But I do think that when we're talking about music and computation, there is quite a deep relationship between the two, to the extent that the process of a piece of music developing as new parts come in and are added, or are subtracted, or are transformed with new and more interesting variations, that process is very similar to that of iterating on a program. So what I want to do is build another piece in front of you, but play it as I'm building it, so you can hear that correlation between the act of editing and incrementally improving a program and the development of a piece of music. So this is In the Mood, if you know it. Right, so to start with, I'm just playing the bass line and nothing else. So I should do something a bit more interesting. So let's start playing arpeggios, so it's going to get reevaluated. So play a bit more interesting now. That's the bass part, so it should probably be lower. Bass shouldn't really be just a fixed thing, because I want it to walk over the different chords, so I really need to make it a function and map it over my chord progression. So I'm going to map then the bass line over 0, 0, 3, 0, 4, 0, which is the standard blues chord progression, but I need to make bass into a function, so I'll use a little bit of a brief Clojure notation, sorry, to do that, and then say where the pitch is from the bass note of the progression. So let's hope this works. So when we next come around, it should start to do that. Right, so we're walking on the fourth, and we'll be back again. And we're going to go to the fifth, for people who know that. The fifth, and then we're going to return back to our home. Include a beat next time round as well. Make it a bit faster in a second. So let's see what we do here. So we should probably also add the actual hook. Map then hook over tonic. So that's the chord progression. So it's just going to play just plain chords the first time round to make sure we've got it right, because honestly I'm not sure we have, right? So let's see how that goes. So we should just hear like a big kind of plain chord. Cool. And we've sped it up a bit, so it's going to hit the bass note of the chord again. We want to play that like In the Mood, kind of cool arpeggiated melody, so I'm going to take the vowels of each chord, the actual notes, I'm going to sort them and I'm just going to cycle through them, but I need to do a bit more serene before we can play it, so we'll loop around once more. Just playing a note for now. Which is something that can very easily happen, right? Musicians might notice, right? It's very straight, just hitting the beat. And that's partly because I'm very white, but also because I haven't added swing to it. But I can fix that a little bit. It'll take just a little bit longer to do that. So what I can basically do is I can use the same scale function that we used for scales, and I'm going to make the first half of the note bigger than the second half, which is kind of a crude definition of swing. So I'm going to do that, and just to give a bit of a pop at the same time, we'll go up a key. That's how it works, right? Oh no, it didn't. Alright, let's just go to the version of it I have there. Right, so you can hear the swing go, right? So you can see this line is the line I was trying to write, where I make the first note 2/3 and the second one 1/3. Go back into C major. Keep playing, yeah? More stuff with it. So I'm hoping to do another change, which is just to go from playing the individual notes in the chord to just repeating the chords. So just give a bit of a variation and a feel to what we're doing. Change the key again. Thanks very much.
Okay, we have time for questions or music requests, whichever one you want to do.
It's a cliche. That's part of the ethics of software music is that you can't play Stairway to Heaven.
Okay.
Hi, thanks for that. That was amazing. I'm wondering, relatively, time it takes to learn to play an instrument versus time to learn how to do music like this, relative differences?
I mean, I think you definitely get instant feedback much, much better just from learning a physical instrument. The difference probably with this is that I can do things with this that I can't physically play. Now, that might be because of my own shortcoming as a musician, but if I want to experiment with multiple parts or different sounds or different kind of production as part of it, I have the power of accumulation of I can concentrate many versions of myself on one version of the code over time. I can, I have unit tests for the music theory version of it. I can kind of have feedback cycles that lets me concentrate a whole bunch of effort into one iteration. You can't really get that with the physical instrument. You still have to play the last chorus, even though it was just the same as the first chorus, and it's redundant. But yeah, I'm not trying to disrupt music or replace learning an instrument with learning to code or anything like that.
Others? Don't be shy.
Hi. How different the process would have been not using a functional language?
So how different? So I think the thing you have to do this kind of structure is that you have to represent the music as some kind of data. So I think if what you had was, I don't know, like a side affecting functions that were called and then with sleeps and so on, I think it would be implausible to actually plug everything together. So I don't think you have to use Clojure or Haskell or whatever, but I do think you need that functional design approach where you take your music and represent it as data, because only once you have it as a first-class citizen within your program can you mess around with it.
Someone on this side, I think, had a question. Oh, good.
So do you use this framework to compose your own music?
Yeah, I use it to make my music, or I guess partly to music that I maybe have composed over years but never been able to actually put in a permeable form. Yeah, I do that. And it works best, I guess, if you're trying to produce electronic sounds because of the uncanny valley problem. So bells actually happen to be close enough, you can get close enough that if you hear a bell and it's a synthesized bell, it'll probably still sound good. If you try to put the same level of effort into synthesizing a violin, it'll sound awful because it won't quite be a violin. So electronica works very well, especially things that are unfolding with complex repetition over time. I can tweet links to examples if you're interested.
Did this approach to music make you appreciate the composers more?
Yes, because it's really hard to keep in your head even when you have all the benefits of coding, right? You look at the functional transformations and you see how things map and you make mistakes, and it really is hard enough with all the leverage of modern programming. So to me, yes. But I think it depends a little bit on your point of view. So some people view deconstruction as destruction, right? That by understanding things or taking them apart, it ruins some of the mystery. I'm not like that. Partly, I guess that goes along with being a programmer. But I'd imagine that if you didn't like to analyze how the bits worked, maybe you would find it took something away.
Last question, maybe?
Thanks a lot. I was just curious about the sound, the sort of pianoistic sound that you generated and how you did that.
The piano, I cheated and used it as a sample one. So there's on freesound.org, not Freesound. Yes, sorry, Freesound. It has like a library of samples that people can use. So I thought I'd try one where I synthesize it from scratch and maybe one where I use the real sound.
I have one question. As a user of another functional language, Python, is this a ploy to keep Clojure alive?
I've deliberately steered away from engaging in any kind of language wars. I think it maybe makes a good case for, probably as it happens, both Python and Clojure being data-centric languages, and that the interactivity you get from, I guess, the Python tooling with Jupyter notebooks and so on as being a good way to experiment. So I think it probably, if anything, to just make a plea for peace and love between us, Sid, that it's, if anything, a statement in favor of both the Python and the Clojure way.
Awesome. Thank you very much, Chris. If you have questions, please come up.